Hello everyone, and welcome back to some more reverse engineering learning. Today I'm going to talk to you today a little bit about what I've recently learned about Ret2Shell sort of solves in CTF plane challenges. So the most common one you'll find in beginner challenges is the return to win, where there's a win function in the binary, and then we have to call that, jump to it, and it will give us the shell. Return to shell code is a little differently, where we have to somehow put the shell code in memory through input, something like that, and then we have to somehow jump to it in order to get a shell and capture the flag. So the challenge I have here as a demonstration is from B-sides 24. It says, what's your name? And then you write something in there and it gives you a little greeting, like name, hello, and then, returns it. Smells obviously like a buffer overflow. So this, we aren't given the source code for this one. So yeah, we can see the main here. We have a little local array of our characters. It writes to it and prints to it. But in the functions table here, there's no win, no shell code, nothing that'll open it for us. So we have to manage to do that for ourselves. And so the tricky part here is in the return to win challenges, you can get the address of these functions, and they're quite static. There are some protections against that, but we're not going to cover that here. So, we can ask, what's the memory address of the win function, and jump to it. That's fine, but in this case, we don't know where to jump to. The reason being is inside main, if we plant the shellcode inside this buffer here, it's very difficult for us to tell exactly where that is in memory. So I'll show that to you here. I have it running in the background here, and this buffer is at the base pointer -50, and we can see here, this is the address. I'm just going to quit and run it again, and we're going to ask it the same thing. Where is this buffer, this address? And we're going to ask it, and we see that we get a different address. So 7890 is the end couple hex, and we'll just do it one more time. So we get 4D80. So it makes it very difficult, unlike the return to win challenges, to say, hey, what's the address of the win function or some other function, and we can just jump straight to it. We have no way, if we inject our shellcode, to just point to where this local 58 or the buffer that we're going to inject our shellcode into. It becomes quite difficult. So that's where we're going to have to look at using something else. And a cool way to do this is utilizing ROP gadgets. So ROP gadget is a tool that will analyze a binary, and it'll print you all the addresses of little bits of assembly that end in return. So we can use these to construct, more complex payloads. And so a really cool exploit for this one is, I'll put a picture up on screen. So what we're going to do is we're going to fill up the local buffer. We're going to overflow it and change the return address to be one of these pieces of ROP gadget code. So the particular one that we're going to use is, I have to double check here, 40115E. The piece that we're particularly interested in is this one here, jump to the stack pointer. And what we're going to do is just a little refresher that the stack pointer points to where the current top of the stack is allocated to. So when the current frame, when you leave or return from the current stack frame, it collapses, and this stack pointer will jump back to where it previously was. And likewise, when you call something, this stack pointer will grow towards the smaller addresses. But what we're going to do here is we're going to try and use the stack pointer to execute our shellcode. Remember, there's a few key registers and pointers. So the stack pointer, which just points to the top of the stack where the allocated memory is, and that grows. There's the instruction pointer of the current instruction to execute, and then as well the base of the current stack frame. But that's okay, I'll put some pictures up. And so what we're going to do is we're going to tell the instruction pointer to start executing from the stack pointer. So that depends upon us having the stack frame collapse, and then the stack pointer we want to be our shellcode. So that looks a little something like this. I'll put a picture up here. So just before we execute, we can have a look at the current stack pointer and see a whole load of NOP slides, the 0x90. So that's going to be our padding all the way up, and then the red rectangle in the middle is the address of the ROP gadget. And so the stack pointer is, before it gets executed, is pointing to this top address we see on the screen, and then after it, once we call the return, the stack frame collapses, and we jump in with the rectangle, we jump to the RSP, and then what that causes is us to start executing instructions where the stack pointer now is. And we can see there's a few more NOP slides just after, below the rectangle, and then it goes on and executes our shellcode. So the final exploit looks a little bit like this, and we can see it in action. So if we go over, it's currently at the breakpoint in here just before the return. So we've got a payload that looks like this. So we have some padding up until the return address that we want to override. We override it with the address of our ROP gadget, add some more padding, and then we put our shellcode at the end here. So when the stack frame collapses, it's going to point to this information here, and we can see that in action. So if we open this window and we pay attention to here, so this currently points to the top of the stack at this address 4D80, and we're going to execute a little bit. So we ignore that one, hit the leave, and then we can see here that changed. The stack pointer collapsed, and then we're going to follow the next instruction to this gadget, and then that changes. Boom. We've now gone and hit this 4D0. So now the stack pointer has shrunk, and then the instruction pointer is here now, because we told the instruction pointer, hey, go now and start executing from where the stack pointer is. And then there's a whole load of NOPs here. I'm not going to go through all of them, but we eventually get our shell. There we go. And so this works on the remote. This is a bit complex for me to understand. It took a while to wrap my head around, but I thought it was really cool. And if you have any more information or want to share some tips, let me know. Thanks.